This is a problem from Chapter 27. We're looking at a linear regression problem, and we're getting started with introducing this notion of hypotheses testing. So first, what we have is we have a poll that was taken where, I guess, periodically or every year, almost every year, they collected data for the following question. You know, if your party nominated a qualified person for president who was a woman, would you vote for that person? And what we're trying to do is see, is there an association, a linear association between the year, or as time moves on, and the likelihood of people saying yes. So here's the data. It looks quite linear. A little hiccup here somewhere in the late 60s. Who knows what that would be from. But anyway, what they did is they already did all the computations for us. We have the computer printout right here. So we really pretty much have all the data. All we need to do is some thinking. So it says, explain in words and numbers what the regression says. So for number one, the regression, I think it's percent, we could say percent yes. Okay, and remember, put a hat on it. So the y-intercept, they don't say constant this time. They actually say y-intercept, which I think is nicer, is negative 5.583 plus the slope, almost 1, 0.999 times the year. Okay, so that's what the regression says. Let's see. So according to the model, we could say the percent, sorry, I'm taking kind of sloppy, but the percent of people willing to vote for a qualified woman. I guess that might leave out Sarah Palin, or I should say female, to be a little bit more professional, maybe. Okay, candidate for president. Increases by about 1%, right? 0.999 if we round, about 1% per year. Okay, so basically, remember that when we describe a model, oftentimes the slope is the most important thing to describe because that's describing the change. Okay, now the second one says, state the hypotheses about the slope. So both numerically and in words. So the issue here is that if we were going to do a test, what we want to do is make sure that this observed linear association that we see is not due to randomness. You know, if we randomly selected again, which would be hard to do if we went back in time and did a poll, would next time we get something more like this, and the time after that something more like this, and in general the slope would be 0. Okay, so that's sort of the what we're trying to get at when we do a hypotheses test. We just want more concrete evidence that there truly is a linear relationship. So here we would say something like there has been no change in the percent of people willing to vote for a female for president. Okay, and the parameter would be beta 1 equals 0. We're saying the slope of the model for the entire population would be 0, that the line would be 0. We're going to say that, and then we're going to look to see if there's evidence that, I'm just going to say it's just, there has been a change. Okay? Dot, dot, dot. Same thing as above. And then here we would say beta 1 is not equal to 0. Okay, so that's the basis for our test. Okay, so I think 3 says, assuming the assumptions are okay, perform a hypotheses test. So let's look at the model first. For 3, what we would say is that if we sampled, we're able to go back in time. Alright, so we'd need a time machine to do this. So again, you have to use your imagination. If we sampled over and over again, according to the null hypothesis, if the null hypothesis was true, we would get slopes that were somewhere close to 0. Okay, think of, I've just been doing this lately, think of this model as a target. Okay, and if we were a dart thrower, if you were an expert dart thrower, you would expect to hit close to the bullseye all the time if you're an expert. And so if the null hypothesis was true, we would expect to hit very close to the hypothesized value most of the time. If the dart thrower threw a dart way out here and missed, that would start to make us suspect maybe he or she is not an expert. Same thing here. If we get a sample value that's way out here, that would start to make us think maybe the null hypothesis is not true. Okay, so the way we do that is our sample statistic is the slope. So our sample statistic is 0.999 or 1. Okay, so we need to know the size of the standard deviation. Okay, so we're going to say that T is the sample statistic, B, minus the hypothesized value, divided by the standard error of B. Okay, so this is going to be 0.999 minus 0 divided by, and if we go up to the computer printout, here is the standard error. Okay, so it's 0.0661, 0.0661, and that's going to equal, it's already given to us, 15.1, or excuse me, 5.1. So that's like that's 1, 2, 3, 4, 5. So that's way out here. So clearly there's something going on. Okay? So the p-value is the probability that t is, actually it's 2 times the probability that t is greater than 5.1. Why do I say 2? Because up here we turned it into a two-tailed test, when we said there's it's not equal to 0. We could have said greater than, but it was really asking if there's been a change. So in any event, the p-value either way is going to be 0. It's 0.0001. So 0.0001. Okay, so we would say something like the p-value is very small, so we reject HO. There is strong evidence that the percentage of people willing to vote for a qualified female candidate is increasing. Okay, so that's how you would do a hypothesis test when you are given the computer printout. Okay, so now the fourth question, I mean, you should know that I kind of like, when we reject, I'd kind of like to do a confidence interval, because I'd kind of like to know by how much. What we know is it's going to be 0.999 plus or minus some margin of error. Okay, so we could say how that slope may vary, but what they're asking us to do is interpret r squared. Okay, so that's r squared tells us how useful the model is. Okay, how useful is the model? Essentially, let's see, explain what r squared for this. Okay, so let's look. R squared is 94.2%. So that means 94.2% of the variation, the change in the percent people saying yes, is explained by time. Is explained by year. Okay, so 94, that's quite a bit. 94.3% of the variation in the percent of people willing to vote yes for a qualified female candidate for president is explained by the year. And what we mean by explained in this case is not cause. It means that year it can be used to predict. So we can put a line through here and predict. Okay, so if we're way out here, we're already at 90%. Okay, so society's changed a lot. We probably want some more data points to make sure that that's continuing, that it's not dropping. But the key here, I think, for this question is qualified. Okay, so that's how you do this problem. I hope that helps.